So the mass of a planar lamina, well, so number one, so you might remember we did this integration back in Calc 2, finding the mass of a wire from A to B. We have this piece of wire for which we calculated its length, and we call that delta x. All right, so that and well, of course, that wire, that I mean, it could be a copper wire or whatever it is, has a variable density. You know, it's not a material manufactured perfectly so that the density is constant. Otherwise, I mean, just multiply delta x times b minus a and you got it, right? I mean, so we got that the mass for this wire was the integral from a to b of some function rho of x with respect to x, and that dx is really the delta x, the tiny piece of wire that we use as a partition to add infinitely many of those by multiplying, you know, mass equals density times, well, length. So in this case, that we call that linear density, because that's the density over one dimension, which is kind of weird because the density that you are used to work with already in physics or mostly in chemistry, I mean, it's density equals mass over volume, which is the amount of mass that is contained in a given volume. That's the density, right? I mean, we're talking 3 dimensions, volume, milliliters, liters, or whatever, centimeters cubed. Not like linear dimension or superficial dimension, which is what we're going to do this time. So we're going to take it from where we left off back in Calculus 2 for the linear density. So in this case, we're going to look at the mass of a surface given its density, which in this case, that density function is not just going to be a function rho of x, it's going to be a function rho of x, y. It's a function of 2 variables, all right? And well, the formula looks exactly the same. Rho, I mean, this time we have a double integral. We have the usual dA, which can be dx dy or dy dx, depending on the complexity of the region over we're integrating. In some cases, it's okay to integrate dy dx because the region over we're going to integrate, it's vertically simple. But if it's not vertically simple and then it's horizontally simple, then we change the order, we reverse the order to dx dy. And well, let's look at one example and see what are we going to get about this. All right, so number one, we're given, they're asking us to find the mass of a triangular lamina with vertices at the origin 2, 3 and 4, 0. Given that the density is given by rho of x, y equals x plus y, x and y are measured in inches and rho is measured in pounds per square inch. All right, so which is units of mass per, well, not per unit of volume, but rather unit of area, because this is superficial density. All right, well, so number one, let's plot the points that form that triangle. So number one, that's the origin, 0, 0, 1, 2, 1, 2, 3, 2, 3, and 4, 0. So that's our region. So we are finding the mass of this triangular lamina actually. However, well, number one, let's set up the mass integral first of all. So mass m equals to the double integral over the region R, which is this region given by these 3 vertices of the triangle. And well, that's the function rho of x, y dA, which in this case is the integral, double integral actually, of the function x plus y dA. Well, not dA. Well, let's determine whether it's going to be dy dx, which is what we usually do, or dx dy. We'll find out. So number one, let's look at this triangle right here. Is it vertically simple? All right, it's vertically simple if we trace vertical lines and throughout the entire region the same function is at the top and the same function is at the bottom. However, did you see this cusp right here? That's where a new graph begins, and in this case, oh no, this is not going to be vertically simple, right? To begin with, let's find out whether it's horizontally simple. Well, for the horizontally simple, check. So from left to right, do I have the same leftmost and the same rightmost graph? So in this case, it is horizontally simple. So we will have to go the order dx dy. All right. So let's see. Dx dy, and well, so for dx dy, that means that the innermost integral, this innermost integral, which is with respect, which we will integrate with respect x, it has to be a function of the of the variable that is in the outermost integral. That is, our limits will be set as a function of y. So we need to describe these two diagonal lines here as functions of y. So number one. So this is the point 0, 0. This is the point 3, 2, or no, 2, 3 rather, not 3, 2, and 4, 0. So, well, this first line right here, the leftmost, it's a diagonal line. Y equals to, how about 2/3 x? Because it rises 2 units and it runs 3 units. I mean, rises 3 units. Hold on, I got the reverse. Yes, I have it upside down. It rises 3 units and runs 2 units. All right, that's 3/2 of y. Right? Hold on, not y. It's x. 3/2 of x. All right. So I was looking at my other notes, so never mind. Now, what about the second equation? Well, we have a couple of points. We can do the slope, which is 0 minus 3. That is y2 minus y1, which is m equals to 0 minus 3, and x2 or minus x1, that's 4 minus 2, that's negative 3/2, all right? And well, using the point slope form, y minus y1 equals m times x minus x1, that's y minus, I'm going to use this point because it contains a 0. That's going to be a lot easier to work with. Y minus 0 equals to negative 3/2 x minus 4. Okay? And well, so I'm going to leave it. So y equals negative 3/2 x, and negative times a negative is positive. 3 times 4, which is 12 over 2. Is that a 6? So those are the two equations in this case in terms of x. However, we will have to solve these two equations in terms of y because our inner limits of integration, our first integration is with respect x, and that has to be functions of the variable that is the outermost integral, in this case functions of y. Well, the first one, multiply both sides by 2/3, that's x equals to 2/3 y, and here we need to add 6 to both sides, or rather subtract 6 to both sides. That's going to be y minus 6 equals to negative 3/2 x, and multiply both sides by negative 2/3. This is going to be x equals to negative 2/3 y. Negative times a negative, again it's positive. 6 times 2, that's 12. Divided by 3 this time, it's plus 4. So we got the lower limit and the upper limit, which in this case is the lower limit will be the leftmost and the upper limit will be our rightmost. That is, that's going to go from x equals to 2/3. Y, let me write it, to negative 2/3. Y plus 4. And the limit with respect to y, that's going to go the lowest y value, which in this case is 0. And what's the largest value of y when we do, isn't it y equals to 3? So this will be the integral that we will have to evaluate. And yes, it's not going to be an easy integral. In fact, I'm going to do only one part of it. So let's integrate x plus y with respect to x. So that's going to give us the integral from 0 to 3 of the integral of x with respect to x. That's x squared over 2 plus y plus xy. And that goes from the lower limit, which is 2y over 3 to negative 2/3 y plus 4 dy. Alright? And again, notice that when we integrate a function that contains more than one variable at a time, we are applying the fundamental theorem of calculus only on the variable with respect to which we did the integration. That is, in this case, we are going to plug in these limits of integration, upper and lower, to the variable that we did in this case, which is only the x. Leave the y alone. All right. So again, I will keep highlighting this all the time because this is a very common mistake to just substitute this upper minus lower on every single variable you see. So just so we can, so this is highlighted so you don't do this on the homework, on the exam, etc. Well, so this will be the integral from 0 to 3. So that's going to be, no, that's not going to be enough space. It's going to be here. The integral from 0 to 3. That's, okay. Upper limit, which is negative 2/3 y plus 4 squared over 2 plus x, which is still upper limit. That is negative 2/3 y plus 4 times y. Notice everything is in terms of y so far, right? So that's how we know that we are doing the correct substitution, the correct evaluation. And then so that's minus 2/3 y quantity squared over 2 plus y times, or rather 2/3 y times y dy. All right. Well, I mean, even though we're doing the integral in a way, the easy way, the easy setup rather, I mean, going as the region being horizontally simple, because I mean we could have done it the other order, dy dx. The thing here is that dy dx, we would have actually had to split the integral into two regions. So that is, write two double integrals, which in this case it's not going to be efficient. And even if you do it the other way around, you will have two double integrals and the limits will still look like these linear equations. I mean, this is like the easiest way, even though the first evaluation looks hard. So you will have to square this binomial, divide by 2, multiply, distribute, square, divide by 2, and multiply. So for this, I will just give you the answer. This is equal to 18. All right. So the mass of this triangle with that given density function is 18 units. And in this case, well, since it's mass and this is in, what's the units? That's actually pounds, right? Just going with the correct units. All right, let's look at the next example. The next example is about physics. Well, this is not the physics I was talking about. So this is just the fact that physicists use this idea of having regions to determine the total charge, on a region, instead of finding the entire mass of a rectangle or a surface. I mean, they're finding the total charge on that given plane or surface if it's in 3D, well, depending on the situation. So charge is a lot of charges are distributed here along, distributed over the triangular region formed by these 3 points. Okay, let's plot the points. Let's see what's going on. Well, this one, I promise you, this one is going to be integrable nicely instead of the other one. So that's the point 0, 1, 1, 1, and 1, 0. So that's going to be the triangle in this case. But the good thing, check the region. It's both vertically simple and horizontally simple. So in this case, we can set up our equation in the way that we want. All right? So the charge density is given. It's given by rho of x y equals x times y. We're going to integrate that in a second. In the meantime, let's analyze our region in 2D right here. Okay. So this horizontal line, because of course, we'd rather go with vertically simple, because usually we integrate in the order dy and then the x. So that means the innermost integral, which is an integration with respect to y, has to have limits with respect the outer integral, which in this case functions of x. So in this case, well, we can describe this linear equation right here. This is a diagonal line with the points 0, 1 and 1, 0. The slope m equals 0 minus 1, which is negative 1, over 1 minus 0, which is 1. The slope is negative 1. And well, we can use any point. I'm going to use a second point. So y minus y1 equals m times x minus x1. That's y minus y1, which is 0, equals m times, which is 1, negative 1. X minus x1, which is 1. That is y equals negative x plus 1. And it's we can see this line has a y-intercept at 0, 1, and it has a negative slope. So let's see. So the total charge, instead of saying the whole mass right here, that's going to be the total charge will be the double integral over the region R of the electrical density given by rho x y dA for now. Well, in this case, I don't really want to go about changing the equations in terms of y. It's not going to be the most complicated thing, but if it's in this case a vertically simple region, let's check it. It's vertically simple. The horizontal line is always at the top, the diagonal line is always at the bottom. So let's go with that. All right. So number 1, double integral x y. We're going to go dy dx. And well, in this case, what's the upper limit? What's the lower limit? Well, the lower limit is the diagonal line, negative x plus 1. And the upper limit will be this horizontal line, y equals to 1. All right? And for the limits of integration, for the outermost integral, that is the limit with respect to x, that goes from 0 to 1. We can see that from the graph, all right? Let's evaluate this one. So the integral of xy with respect to y, so that's going to be integral from 0 to 1, xy squared over 2, evaluated from negative x plus 1 to 1, dx, and well, upper limit minus lower limit, but again, These limits of integration, 1 and negative x plus 1, will go only to the y. Will be plugged into the y only because we did the first integration with respect to y. That is, that's the integral from 0 to 1. So that's going to be number 1. How do we evaluate it? Okay, so that's x over 2 that multiplies some y squared, that is 1 squared, minus x over 2 that multiplies negative x plus 1 squared dx. All right. Well, this one we will actually simplify. Well, number 1, notice x over 2 is common to both terms right here. So in this case, 1 squared, which is 1, times x, that's an x, and then the common denominator, which is 2. I'm going to write this in terms of a one single fraction. So that's the integral from 0 to 1. And that's everything over 2. 1 squared, which is 1, times x, that's just x. And then whatever polynomial we end up by squaring this binomial times x. And well, this is a binomial square. You can just use the formula to square the binomial or FOIL it, whatever you feel more comfortable with. I think squaring the binomial is going to be a lot quicker. So that's a minus x times x squared minus 2x plus 1 dx. Let's simplify all this. A lot of stuff is going to get simplified from 0 to 1. X minus x cubed plus 2x squared minus x over 2 dx, and see how a couple of terms get cancelled, which is great, right? Because doing the fundamental theorem with too many terms, that's going to take a long time to evaluate. All right, so let's see what's next. Okay, so we got the integral. Let me have the 1/2 outside. 1/2 the integral from 0 to 1, and in this case the terms that survive are the 2x squared minus x cubed. So, well, that's the integral. Let's integrate that. That's 1/2. So that's 2x cubed over 3 minus x to the 4th over 4. That evaluated from 0 to 1. And well, upper limit minus lower limit, 1/2, 2/3, 1 cubed minus 1 to the 4th over 4 minus, do we agree that this would be a big 0 when we evaluate the lower limit of 0 for this couple of terms? That's fine, that's valid. And well, after simplifying all this, that should give us 5 over 24. And in this case, the units are coulombs, all right, because we're finding well, not the mass, but rather the total charge. All right. And